The universe is a place of endless wonder, filled with mysteries that defy our understanding. Among its most enigmatic inhabitants are supermassive stars, cosmic giants that burn brighter, live faster, and die more explosively than anything else in the cosmos. These stars are not just big, they are colossal, with masses hundreds of times greater than our Sun. But their size is only the beginning of their strangeness. Supermassive stars behave in ways that challenge everything we think we know about the universe. From runaway stars hurtling through galaxies at unimaginable speeds to stellar cannibals devouring their neighbors, these cosmic titans are rewriting the rules of space itself. In this video, we're diving into 30 of the most bizarre and fascinating behaviors of supermassive stars, phenomena so extraordinary they seem almost impossible. So, buckle up and get ready to explore the wild, unpredictable, and utterly mind-blowing world of these stellar behemoths. By the end of this journey, you'll see the universe in a whole new light. Let's begin. Now, let's dive into the first of these cosmic oddities, runaway stars. Imagine a star so massive, so powerful, that it gets literally kicked out of its own galaxy. These are runaway stars, and they're not just moving fast, they're racing through space at speeds that can reach millions of miles per hour. But how does this even happen? Well, it usually starts with a dramatic event, like a close encounter with another massive object, such as a supermassive black hole. The intense gravitational forces can slingshot the star out of its galactic home. Alternatively, a supernova explosion in a binary star system can send one of the stars flying off at incredible speeds, like a cosmic cannonball. The implications of these runaway stars are staggering. For one, they challenge our understanding of how stars move and interact within galaxies. We used to think stars stayed relatively close to their birthplaces, but runaway stars prove that the universe is far more chaotic and dynamic than we imagined. These stellar outcasts also leave behind trails of ionized gas, creating glowing pathways that astronomers can study to learn more about their origins and the forces that propelled them. But perhaps the most fascinating aspect is what these stars tell us about the extreme environments they come from. Runaway stars are like cosmic messengers, carrying clues about the violent events that shaped their journeys. By studying them, we gain insights into the life cycles of supermassive stars and the powerful forces that govern the universe. So, the next time you look up at the night sky, remember, somewhere out there, a runaway star is blazing a trail through the cosmos, defying the rules and rewriting our understanding of stellar dynamics. Now, let's shift our gaze to another cosmic marvel, hypervelocity stars. These aren't just fast stars, they're so incredibly speedy that they can break free from the gravitational pull of their entire galaxy. Picture a star hurtling through space at millions of miles per hour, leaving its galactic home behind forever. But how do these stars achieve such mind-boggling speeds? The answer lies in some of the most extreme environments in the universe. One leading theory suggests that hypervelocity stars are born from close encounters with supermassive black holes. Imagine a binary star system, two stars orbiting each other, wandering too close to a black hole. The immense gravitational forces can tear the pair apart, with one star being captured by the black hole while the other is flung outward at an astonishing speed. It's like a cosmic slingshot, launching the star into the void at velocities that defy imagination. Another possibility is that these stars are the remnants of ancient galactic collisions. When two galaxies merge, the chaotic gravitational interactions can fling stars out into intergalactic space at incredible speeds. These stars become cosmic nomads, traveling alone through the vast emptiness between galaxies. What makes hypervelocity stars so fascinating is what they reveal about the forces at play in the universe. They serve as natural experiments, allowing astronomers to study the effects of extreme gravity and the dynamics of galactic interactions. By tracking their paths, scientists can piece together the history of their origins and the environments that shaped their journeys. So, the next time you think about the stars, remember that some of them are not just twinkling quietly in the night sky, they're racing across the cosmos, breaking free from the very galaxies that birthed them. Hypervelocity stars remind us that the universe is full of surprises, and even the stars themselves can defy the rules we thought we understood. Now, let's dive into a behavior that sounds like something straight out of a cosmic horror story: stellar cannibalism. Yes, you heard that right. Some supermassive stars have a habit of devouring their neighbors. Imagine a star so massive and powerful that it can literally consume smaller stars or even planets that wander too close. It's a brutal process, but one that plays a crucial role in shaping the universe as we know it. When a supermassive star encounters a smaller star or planet within its gravitational reach, the immense pull of its gravity can strip away material from the smaller object. Over time, this stolen material accumulates onto the supermassive star, causing it to grow even larger. It's like a cosmic version of survival of the fittest, where the biggest and strongest stars dominate their surroundings. This process doesn't just affect the star doing the consuming, it has ripple effects throughout the entire star system. For one, the smaller star or planet that's being consumed is often destroyed, leaving behind a trail of debris. This debris can form accretion disks around the supermassive star, which can eventually lead to the formation of new planets or even smaller stars. In some cases, the stolen material can also trigger intense bursts of radiation or stellar winds, altering the environment of the entire system. But what's truly fascinating is how stellar cannibalism can lead to the creation of even more massive stars. By gobbling up smaller objects, supermassive stars can push the limits of how big a star can theoretically grow. Some of these stars become so massive that they challenge our understanding of stellar physics, forcing scientists to rethink the rules that govern these cosmic giants. Stellar cannibalism also raises intriguing questions about the fate of star systems. Could a supermassive star eventually consume all the objects around it, leaving behind a lonely, bloated giant? Or could the process of cannibalism trigger new cycles of star formation, creating a dynamic and ever-changing cosmic landscape? As we continue to explore the universe, behaviors like stellar cannibalism remind us just how dynamic and unpredictable the cosmos can be. It's a place where even the stars themselves are locked in a constant struggle for survival, shaping the universe in ways we're only beginning to understand. Now, let's shift our gaze to one of the most explosive and awe-inspiring events in the cosmos: supermassive star collisions. Picture this: two colossal stars, each weighing hundreds or even thousands of times more than our Sun, hurtling toward each other in a cosmic dance of destruction. These collisions are rare, but when they happen, they unleash unimaginable energy and reshape the fabric of space itself. When two supermassive stars collide, the result is nothing short of spectacular. The sheer force of their impact generates shock waves that ripple through the surrounding space, heating up nearby gas and dust to extreme temperatures. This collision can trigger a massive explosion, releasing more energy in a few moments than our Sun will emit over its entire lifetime. It's like a cosmic fireworks display on a scale that's almost impossible to comprehend. But the aftermath of these collisions is just as fascinating as the event itself. In some cases, the two stars merge to form an even larger star, a true titan of the universe. This newly formed star can be so massive that it pushes the boundaries of what we thought was possible for stellar sizes. These mergers also create intense magnetic fields and powerful stellar winds, which can influence the surrounding star systems for millions of years. The energy released during these collisions doesn't just vanish into the void. It has a profound impact on the surrounding environment. The explosion can trigger the formation of new stars by compressing nearby gas clouds, effectively jump-starting the birth of an entire stellar nursery. At the same time, the shock waves from the collision can disrupt existing star systems, altering their orbits and even ejecting smaller stars into the depths of space. What makes these collisions so intriguing is how they challenge our understanding of stellar physics. The conditions during a supermassive star collision are so extreme that they create environments unlike anything else in the universe. Scientists study these events to learn more about the limits of star formation, the behavior of matter under extreme pressure, and the origins of some of the most energetic phenomena in the cosmos. As we continue to explore the universe, supermassive star collisions remind us of the incredible forces at play in the cosmos. They're a testament to the dynamic and ever-changing nature of the universe, where even the mightiest stars are not immune to the pull of gravity and the inevitability of change. And as we uncover more about these rare events, we gain a deeper appreciation for the delicate balance that shapes the stars and galaxies around us. Next, we'll turn our attention to another strange behavior of supermassive stars, their ability to warp spacetime with their incredibly strong magnetic fields. Stay tuned as we explore the magnetic monsters of the cosmos. Now, let's dive into one of the most mind-bending behaviors of supermassive stars, their ability to become magnetic monsters. Imagine a star so powerful that its magnetic field isn't just strong enough to influence its immediate surroundings, but can actually warp the very fabric of spacetime. These stars are like cosmic magnets on steroids, and their magnetic fields are so intense that they defy our everyday understanding of physics. The magnetic fields of these supermassive stars are millions, sometimes even billions, of times stronger than Earth's magnetic field. To put that into perspective, if you were to bring a compass anywhere near one of these stars, it wouldn't just point north, it would likely be ripped apart by the sheer force of the magnetic pull. These fields are generated deep within the star's core, where extreme temperatures and pressures cause charged particles to move in chaotic, high-energy patterns. This movement creates magnetic fields that extend far beyond the star's surface, reaching out into space and influencing everything in their path. But how do scientists measure something as vast and powerful as a supermassive star's magnetic field? It's not as simple as sticking a magnetometer into space. Instead, astronomers rely on indirect methods, such as observing how the star's light interacts with its magnetic field. When light passes through a magnetic field, its properties can change in predictable ways, a phenomenon known as the Zeeman effect. By analyzing these changes, scientists can estimate the strength and structure of the star's magnetic field. Another method involves studying the star's X-ray emissions, which are often influenced by the magnetic field's intensity and orientation. The effects of these magnetic fields are nothing short of extraordinary. They can shape the star's surroundings, creating vast structures like magnetic loops and arcs that stretch across millions of miles. These structures can trap and accelerate particles, producing intense radiation that can be detected across the galaxy. In some cases, the magnetic fields are so strong that they can even warp spacetime itself, bending light and altering the paths of nearby objects. This phenomenon, known as gravitational lensing, allows astronomers to study distant objects that would otherwise be hidden from view. But the influence of these magnetic monsters doesn't stop there. Their fields can also impact nearby star systems, disrupting the orbits of planets and even triggering star formation in surrounding gas clouds. In extreme cases, the magnetic fields can strip away the outer layers of nearby stars, leaving behind exposed cores and altering their life cycles. These interactions create a dynamic and ever-changing environment where the magnetic fields of supermassive stars play a central role in shaping the cosmos. What makes these magnetic monsters so fascinating is how they challenge our understanding of the universe. They push the boundaries of what we thought was possible, showing us that even the most familiar objects like stars can behave in ways that are utterly alien. By studying these magnetic fields, scientists gain insights into the fundamental forces that govern the universe, from the behavior of matter under extreme conditions to the intricate dance of spacetime itself. As we continue to explore the cosmos, these magnetic monsters remind us that the universe is full of surprises. They're a testament to the incredible diversity and complexity of the stars that light up the night sky, and they inspire us to keep asking questions about the mysteries that lie beyond our reach. Next, we'll explore another strange and fascinating behavior of supermassive stars, starquakes. These violent shifts on a star's surface reveal secrets about what's happening deep within its core. Stay tuned as we uncover the seismic secrets of the cosmos. Now, let's shift our focus to something equally dramatic but far more explosive: starquakes. Imagine the surface of a supermassive star suddenly cracking and shifting, releasing energy equivalent to millions of nuclear bombs. These cosmic tremors, known as starquakes, are like earthquakes but on a scale that's almost unimaginable. While earthquakes shake the ground beneath our feet, starquakes ripple across the surface of a star, revealing secrets about what's happening deep within its core. Starquakes occur when the immense internal pressures of a supermassive star cause its outer layers to fracture and shift. These pressures build up due to the star's intense gravity and the chaotic movements of its core, where nuclear reactions generate unimaginable amounts of energy. When the pressure becomes too great, the star's surface can't hold it in anymore, leading to violent shifts that send shockwaves rippling through the star. These quakes can last for minutes or even hours, releasing energy that can be detected across vast distances in space. But how do starquakes compare to earthquakes? On Earth, earthquakes are caused by the movement of tectonic plates, which float on the planet's molten mantle. In contrast, starquakes are driven by the internal dynamics of a star, where the balance between gravity, pressure, and magnetic forces is constantly shifting. While earthquakes can be devastating, starquakes are on an entirely different level. The energy released during a starquake can be billions of times greater than the most powerful earthquake ever recorded on Earth. What makes starquakes so fascinating is what they reveal about the interiors of supermassive stars. Just as seismologists use earthquakes to study Earth's inner layers, astronomers use starquakes to probe the hidden depths of stars. When a starquake occurs, it sends vibrations through the star's interior, much like ripples in a pond. By studying these vibrations, scientists can learn about the star's density, temperature, and even its composition. This process, known as astroseismology, allows astronomers to create detailed maps of a star's interior, uncovering information that would otherwise remain hidden. For example, starquakes have revealed that some supermassive stars have layers of different densities, with hotter, more turbulent regions near the core and cooler, more stable layers near the surface. They've also shown that the cores of these stars can rotate at different speeds than their outer layers, creating complex internal dynamics that influence the star's behavior. These insights help scientists understand how supermassive stars evolve over time and what happens when they reach the end of their lives. But starquakes aren't just about science, they're also a reminder of the sheer power and unpredictability of the universe. These violent events show us that even the most stable-looking stars are dynamic, ever-changing objects, constantly reshaping themselves under the forces of gravity and pressure. By studying starquakes, we gain a deeper appreciation for the complexity of the cosmos and the incredible forces that shape it. As we continue to explore the strange behaviors of supermassive stars, starquakes stand out as one of the most dramatic and revealing phenomena. They remind us that the universe is full of surprises, and that even the stars we see every night hold secrets waiting to be uncovered. Next, we'll turn our attention to another fascinating behavior: supermassive star pulsations. These rhythmic expansions and contractions offer a unique window into the life cycles of these cosmic giants. Stay tuned as we dive into the heartbeat of the stars. Now, let's step into the rhythmic heartbeat of the cosmos: supermassive star pulsations. Imagine a star breathing, expanding and contracting in a steady, almost hypnotic rhythm. These pulsations are not just random movements, they're a fundamental part of how some supermassive stars behave, offering us a unique glimpse into their inner workings. Supermassive star pulsations occur when the star's outer layers expand and contract in regular cycles, much like the rise and fall of ocean tides. These cycles can last anywhere from hours to years, depending on the star's size and internal dynamics. The pulsations are driven by a delicate balance between the star's gravity, which pulls its material inward, and the pressure from nuclear reactions in its core, which pushes outward. When these forces aren't perfectly balanced, the star begins to oscillate, creating a rhythmic pattern of expansion and contraction. But what causes these pulsations to start in the first place? One key factor is the star's internal structure. In some supermassive stars, layers of different densities and temperatures can create instability. For example, if the outer layers of the star are cooler and denser than the inner layers, they can trap heat and pressure, causing the star to expand. As the star expands, the pressure decreases, allowing the outer layers to cool and contract again. This cycle repeats, creating the pulsations we observe. These pulsations have a profound impact on the star's brightness and structure. As the star expands, its surface area increases, making it appear brighter from our perspective. When it contracts, the surface area decreases and the star dims. This regular change in brightness is one of the ways astronomers detect pulsating stars. By studying these brightness variations, scientists can determine the star's pulsation period, which provides clues about its size, mass, and internal composition. Pulsations also affect the star's internal structure. The rhythmic expansion and contraction can mix material from different layers, bringing heavier elements from the core closer to the surface. This process, known as convection, can influence the star's evolution and even its eventual fate. For example, some pulsating supermassive stars may shed their outer layers more quickly, leading to dramatic changes in their life cycles. What makes pulsating supermassive stars so fascinating is their role as cosmic timekeepers. By observing their pulsations, astronomers can measure distances across the universe and study the properties of space itself. These stars act like lighthouses, their rhythmic flickers providing a steady reference point in the vastness of space. As we explore the pulsations of supermassive stars, we're reminded of the delicate balance that governs the universe. These rhythmic expansions and contractions are not just a cosmic curiosity, they're a window into the forces that shape the lives of stars and the galaxies they inhabit. Next, we'll turn our attention to another powerful force in the lives of supermassive stars: stellar winds. These intense outflows of particles and energy play a crucial role in shaping the stars and their surroundings. Stay tuned as we uncover the secrets of these cosmic gusts. Now, let's shift our gaze to the invisible yet unstoppable force that supermassive stars unleash into the cosmos: stellar winds. These aren't the gentle breezes we feel on Earth. They're torrents of charged particles and radiation, streaming outward at incredible speeds. Stellar winds are one of the most powerful and dynamic behaviors of supermassive stars, capable of reshaping entire star systems and even influencing the evolution of galaxies. Supermassive stars generate stellar winds through their intense radiation and magnetic fields. The energy produced in their cores is so immense that it pushes material from the star's surface outward into space. These winds can reach speeds of millions of kilometers per hour, carrying away vast amounts of gas and dust. Over time, this process can strip away a significant portion of the star's outer layers, altering its structure and even shortening its lifespan. But the impact of stellar winds doesn't stop at the star itself. These winds can extend far into the surrounding space, creating shock waves that compress nearby gas and dust. This compression can trigger the formation of new stars, effectively turning the winds of one supermassive star into the building blocks for future generations of stars. In this way, stellar winds play a crucial role in the life cycle of galaxies, seeding the cosmos with the raw materials needed for star formation. Stellar winds also interact with other stars and planetary systems in their vicinity. For example, if a supermassive star is part of a binary system, its winds can collide with those of its companion star, creating spectacular shock fronts and intense radiation. These interactions can heat up the surrounding space, influencing the conditions for planet formation and even affecting the habitability of nearby worlds. One of the most fascinating aspects of stellar winds is their ability to sculpt the interstellar medium, the vast, diffuse gas and dust that fills the space between stars. As these winds sweep through the galaxy, they carve out bubbles and cavities, shaping the structure of the interstellar medium on a grand scale. These structures can persist for millions of years, serving as lasting reminders of the supermassive stars that created them. Stellar winds also play a key role in the chemical evolution of galaxies. As they carry material away from supermassive stars, they distribute heavy elements like carbon, oxygen, and iron into the surrounding space. These elements, forged in the hearts of stars, are essential for the formation of planets, life, and even future stars. Without stellar winds, the universe as we know it would look very different. As we explore the power of stellar winds, we're reminded of the interconnectedness of the cosmos. These winds are not just a byproduct of supermassive stars, they're a driving force in the evolution of galaxies, shaping the universe on both small and large scales. Next, we'll dive into another explosive behavior of supermassive stars, stellar flares. These sudden bursts of energy can outshine entire galaxies, and their effects ripple across the cosmos. Stay with us as we uncover the fiery secrets of these cosmic eruptions. Now, let's turn our attention to one of the most dramatic displays of power in the universe: supermassive star flares. These aren't just ordinary bursts of energy, they're colossal eruptions that can outshine entire galaxies for brief moments. Imagine the most intense solar flare you've ever heard of, and then multiply its energy by a factor of millions. That's the kind of power we're talking about when it comes to supermassive star flares. These flares occur when the magnetic fields of supermassive stars become twisted and unstable, often due to the star's rapid rotation or interactions with a companion star. When the tension in these magnetic fields becomes too great, they snap, releasing a torrent of energy in the form of radiation, charged particles, and even gamma rays. The result is a flare so bright that it can be detected across vast cosmic distances. While solar flares from our own sun can disrupt satellites and power grids on Earth, supermassive star flares are on an entirely different scale. The energy released in a single flare from one of these cosmic giants can exceed the total energy output of our sun over hundreds of thousands of years. This immense energy doesn't just vanish into space, it has profound effects on the surrounding environment. For instance, the radiation from these flares can ionize nearby gas clouds, stripping electrons from atoms and creating a highly charged environment. This ionization can trigger the formation of new stars or even halt star formation in certain regions by heating the gas to extreme temperatures. In some cases, the radiation from a supermassive star flare can reach nearby planets, potentially stripping away their atmospheres or rendering them uninhabitable. But the impact of these flares doesn't stop there. The charged particles ejected during a flare can travel at near light speeds, creating shock waves as they collide with the interstellar medium. These shock waves can compress gas and dust, leading to the formation of new stars or even triggering supernova explosions in nearby stars. In this way, supermassive star flares act as cosmic catalysts, shaping the evolution of their surroundings in ways we're only beginning to understand. What's truly fascinating is how these flares compare to their smaller counterparts like solar flares. While both are driven by magnetic activity, the sheer scale of supermassive star flares makes them unique. A single flare from a supermassive star can release more energy in a few seconds than our sun will emit over its entire lifetime. This difference in scale highlights just how extreme these cosmic giants can be. As we continue to study supermassive star flares, we're uncovering more about their role in the universe. These eruptions aren't just spectacular light shows. They are fundamental processes that influence the birth and death of stars, the formation of planets, and even the chemical makeup of galaxies. Next, we'll explore another intriguing behavior of supermassive stars' binary systems. These pairs of massive stars orbit each other in a delicate dance, often leading to extraordinary interactions. Stay tuned as we unravel the mysteries of these cosmic duos. Now, let's shift our gaze to one of the most fascinating cosmic partnerships, binary supermassive star systems. Picture two colossal stars, each with masses dozens or even hundreds of times greater than our Sun, locked in a gravitational dance as they orbit one another. These systems are not just visually stunning, they're also laboratories for some of the most extreme and dynamic behaviors in the universe. In a binary supermassive star system, the gravitational pull between the two stars creates a delicate balance. As they orbit, their immense gravity can distort each other's shapes, pulling material from one star to the other in a process known as mass transfer. This exchange of material can dramatically alter the life cycles of both stars. For example, the star receiving the extra mass might grow larger and burn through its fuel faster, while the donor star could shrink or even collapse under the strain. But the drama doesn't stop there. In some cases, the gravitational interactions between these stars can become so intense that they spiral closer and closer together, eventually merging into a single, even more massive star. These mergers are among the most energetic events in the cosmos, releasing vast amounts of energy in the form of light, heat, and gravitational waves. The resulting star can be so massive that it teeters on the edge of stability, often leading to a spectacular explosion or collapse into a black hole. What makes binary supermassive star systems so intriguing is how they challenge our understanding of stellar evolution. Unlike solitary stars, which follow a relatively predictable life cycle, binary systems introduce a layer of complexity. The interactions between the two stars can accelerate their aging, trigger unexpected explosions, or even create entirely new types of stellar objects. For instance, some binary systems are known to produce X-ray emissions as material from one star falls onto the other, heating up to incredible temperatures. These X-ray binaries are some of the brightest objects in the sky, offering astronomers a unique window into the physics of extreme environments. The study of binary supermassive star systems also sheds light on the origins of some of the universe's most mysterious phenomena. For example, the gravitational waves detected by observatories like LIGO often originate from the mergers of massive stars or black holes in binary systems. By understanding how these systems evolve, we can piece together the story of how the universe's most massive objects come to be. As we continue to explore these cosmic duos, we're reminded of the intricate and interconnected nature of the universe. Binary supermassive stars are not just isolated pairs. They're dynamic systems that influence their surroundings, shape the evolution of galaxies, and even leave behind remnants that continue to shape the cosmos long after their fiery lives have ended. Next, we'll dive into the explosive deaths of supermassive stars, where the stakes are as high as the energy released. Stay tuned as we uncover the dramatic final acts of these cosmic giants. Now, let's turn our attention to one of the most dramatic and awe-inspiring events in the cosmos, the explosive deaths of supermassive stars. When these colossal giants reach the end of their lives, they don't fade away quietly. Instead, they go out with a bang, unleashing some of the most powerful explosions the universe has ever seen. These events, known as hypernovae or gamma-ray bursts, are so energetic that they can outshine entire galaxies for a brief moment. To understand these explosions, we need to look at what happens inside a supermassive star as it nears the end of its life. These stars burn through their nuclear fuel at an astonishing rate, creating heavier and heavier elements in their cores. Eventually, the core becomes so dense that it can no longer support its own weight. When this happens, the core collapses in on itself, triggering a catastrophic explosion. In the case of hypernova, the explosion is so powerful that it can release up to 10 times more energy than a typical supernova. This immense energy is often accompanied by a gamma-ray burst, a beam of high-energy radiation that shoots out into space at nearly the speed of light. These bursts are so intense that they can be detected from billions of light years away, making them some of the most distant and ancient events we can observe. But what makes these explosions truly significant is their role in shaping the universe. The elements forged in the hearts of supermassive stars, like gold, platinum, and uranium, are scattered across space during these explosions. Over time, these elements become the building blocks for new stars, planets, and even life itself. Without the explosive deaths of supermassive stars, the universe as we know it wouldn't exist. Gamma-ray bursts also serve as cosmic beacons, helping astronomers map the distant reaches of the universe. By studying these bursts, scientists can learn about the conditions in the early universe and the processes that drive the formation of galaxies. They also provide clues about the nature of black holes and neutron stars, which often form in the aftermath of these colossal explosions. As we continue to explore the universe, the explosive deaths of supermassive stars remind us of the incredible forces at work in the cosmos. These events are not just spectacular displays of energy, they're fundamental to the story of how the universe evolves. Next, we'll explore another fascinating phenomenon: star spots, the massive blemishes on the surfaces of supermassive stars that reveal clues about their inner workings. Stay tuned as we uncover the secrets hidden in these stellar fingerprints. Now, let's shift our gaze to the surfaces of supermassive stars, where massive blemishes known as star spots tell a fascinating story about their inner workings. These spots are like sunspots on our own sun, but on a far grander scale, often spanning thousands of kilometers across. Imagine dark patches on the surface of a star, regions where the magnetic activity is so intense that it suppresses the flow of heat, creating cooler, dimmer areas. Star spots play a crucial role in shaping the brightness of supermassive stars. As these massive stars rotate, the spots move in and out of view, causing fluctuations in their observed light. These changes in brightness can be detected by astronomers, providing valuable clues about the star's rotation rate and magnetic activity. In some cases, the variations caused by star spots are so dramatic that they can mimic the behavior of other stellar phenomena, like pulsations or even the presence of orbiting planets. But star spots aren't just about brightness, they're windows into the magnetic lives of supermassive stars. The intense magnetic fields that create these spots are a sign of the turbulent activity happening deep within the star. By studying star spots, scientists can learn about the internal dynamics of these cosmic giants, including how their magnetic fields are generated and how they influence the star's evolution. Interestingly, star spots can also reveal the age of a supermassive star. Younger, more active stars tend to have more prominent and numerous spots, while older stars may show fewer and smaller ones. This makes star spots a useful tool for understanding the life cycles of these massive objects and how they change over time. As we continue to explore the mysteries of supermassive stars, star spots remind us that even the surfaces of these colossal objects hold secrets waiting to be uncovered. These stellar blemishes are more than just dark patches, they're key to understanding the complex and dynamic nature of the universe's most massive stars. Next, we'll dive into the powerful jets of particles and radiation that some supermassive stars emit, shaping their surroundings in dramatic ways. Stay tuned as we explore the cosmic fireworks unleashed by these stellar giants. Now, let's turn our attention to one of the most spectacular displays in the cosmos, the powerful jets of particles and radiation that some supermassive stars unleash into space. These jets are like cosmic fire hoses, shooting out streams of energy and matter at incredible speeds. often stretching for light years across the universe. But what causes these dramatic outflows, and what do they mean for the stars and their surroundings? The formation of these jets begins deep within the star, where intense magnetic fields and rapid rotation create a chaotic environment. As material swirls around the star's core, some of it gets funneled along the magnetic field lines, accelerating to near light speeds before being ejected from the star's poles. This process is similar to how water spirals down a drain, but on a scale so vast it defies imagination. Once launched, these jets can travel enormous distances, carving through the interstellar medium like a knife through butter. They carry with them not just particles and radiation, but also energy that can heat up and ionize the surrounding gas, triggering the formation of new stars or even entire star clusters. In some cases, the jets can even push away nearby clouds of dust and gas, clearing out vast regions of space and shaping the structure of galaxies. But the impact of these jets doesn't stop there. As they collide with the interstellar medium, they create shock waves that ripple through space, producing bursts of light and radiation that astronomers can detect from Earth. These interactions provide valuable insights into the conditions around supermassive stars and the processes that drive their evolution. Interestingly, the jets themselves can also reveal clues about the star's history. By studying their speed, direction, and composition, scientists can piece together the story of how the star formed, how it has evolved, and what its future might hold. In a way, these jets are like cosmic fingerprints, leaving behind a record of the star's life and activity. As we marvel at the sheer power of these stellar jets, it's clear that they are more than just cosmic fireworks. They are fundamental to understanding how supermassive stars influence their environments and shape the universe around them. Next, we'll explore how some supermassive stars undergo dramatic transformations, changing their very nature over time. Stay with us as we uncover the secrets of stellar metamorphosis. Now, let's shift our focus to one of the most fascinating aspects of supermassive stars, their ability to undergo dramatic transformations, changing their very nature over time. This process, known as stellar metamorphosis, is a cosmic spectacle that reveals the incredible dynamism of these massive celestial bodies. When a supermassive star reaches the end of its life, it doesn't simply fade away. Instead, it undergoes a series of dramatic changes, often culminating in the creation of entirely new types of objects. One of the most common outcomes is the formation of a neutron star. As the star exhausts its nuclear fuel, its core collapses under its own gravity, compressing matter to unimaginable densities. The result is a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. But not all supermassive stars become neutron stars. In some cases, the core's collapse is so extreme that it forms a black hole. This happens when the star's mass is so great that not even neutrons can withstand the crushing force of gravity. The core collapses into a singularity, a point of infinite density where the laws of physics as we know them break down. Around this singularity, an event horizon forms, creating a region of space from which nothing, not even light, can escape. The process of stellar metamorphosis doesn't end with the formation of a neutron star or black hole. These objects continue to influence their surroundings in profound ways. Neutron stars, for example, often spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. These pulsars can be detected from Earth, providing astronomers with valuable data about the star's history and the conditions of its formation. Black holes, on the other hand, are known for their immense gravitational pull, which can warp space-time and influence the motion of nearby stars and gas clouds. In some cases, black holes can even trigger the formation of new stars by compressing surrounding material, creating a cycle of destruction and creation that shapes the evolution of galaxies. What makes stellar metamorphosis so remarkable is the sheer scale of the changes involved. A star that once shone brightly for millions or even billions of years can transform into an entirely different kind of object in a matter of seconds. This process not only highlights the incredible forces at work in the universe, but also underscores the interconnectedness of all cosmic phenomena. As we continue our journey through the strange behaviors of supermassive stars, we'll next explore the stunning rings of dust and gas that sometimes form around these celestial giants. Stay with us as we uncover the secrets of supermassive star rings and their role in the cosmos. Now, let's turn our attention to one of the most visually stunning phenomena in the cosmos: supermassive star rings. These rings, often composed of swirling dust and gas, encircle some of the largest stars in the universe, creating breathtaking celestial displays that captivate astronomers and stargazers alike. The formation of these rings begins with the intense radiation and stellar winds emitted by supermassive stars. As these stars burn through their fuel, they expel massive amounts of material into space. This material, consisting of gas and dust, doesn't simply drift away. Instead, it gets caught in the star's gravitational pull, forming a disk-like structure around it. Over time, this disk can evolve into a ring, shaped by the star's rotation and the forces at play in its immediate environment. But these rings aren't just cosmic decorations. They play a crucial role in the life cycle of stars. The dust and gas within these rings can clump together under gravity, eventually forming new stars or even planets. In this way, supermassive star rings act as stellar nurseries, fostering the birth of new celestial bodies. This process is a beautiful example of how the death of one star can lead to the creation of many others, highlighting the cyclical nature of the universe. Interestingly, the composition of these rings can vary widely depending on the star's history and surroundings. Some rings are rich in heavy elements, forged in the heart of the supermassive star and expelled during its final stages. Others may contain pristine gas from the interstellar medium, untouched by stellar processes. This diversity makes each ring a unique window into the star's past and the conditions of its formation. What's even more fascinating is how these rings interact with their surroundings. The intense radiation from the supermassive star can heat the ring, causing it to glow brightly in infrared light. This glow can be detected by telescopes, allowing astronomers to study the ring's structure and composition in detail. In some cases, the ring's material can also funnel back toward the star, fueling further activity and prolonging its life. As we marvel at these cosmic rings, it's worth noting that they're not just isolated phenomena. They're part of a larger story of stellar evolution, connecting the lives of stars across vast stretches of space and time. From the birth of new stars to the recycling of cosmic material, supermassive star rings remind us of the intricate web of processes that shape our universe. Next, we'll explore another fascinating aspect of supermassive stars: stellar echoes, where light from a star's explosion reflects off nearby dust clouds, creating a cosmic time capsule. Stay tuned as we uncover how these echoes help astronomers piece together the history of the universe. Now, let's shift our gaze to a phenomenon that feels almost like a cosmic whisper from the past: stellar echoes. Imagine a supermassive star reaching the end of its life in a spectacular explosion, sending out a burst of light so intense it illuminates the surrounding space. But here's where it gets fascinating. That light doesn't just vanish. Instead, it bounces off nearby dust clouds, creating what astronomers call stellar echoes. These echoes are like ripples in a pond, carrying information about the star's final moments across the universe. Stellar echoes work much like an echo in a canyon, but on a cosmic scale. When a supermassive star explodes, the light from the explosion travels outward in all directions. Some of this light hits dust clouds, which act like giant mirrors, reflecting the light back toward us. Because light takes time to travel, the reflected light reaches Earth much later than the initial explosion. This delay allows astronomers to observe the same event multiple times, each reflection offering a slightly different perspective. These echoes are more than just a visual spectacle, they're invaluable tools for studying the history of the universe. By analyzing the light from stellar echoes, scientists can piece together details about the original explosion, such as its energy, composition, and even the conditions of the star before it died. It's like having a time machine that lets us revisit and study ancient cosmic events in incredible detail. One of the most remarkable aspects of stellar echoes is their ability to reveal the chemical makeup of the star and its surroundings. The light from the explosion carries signatures of the elements present in the star, and when it reflects off dust clouds, it preserves this information. This allows astronomers to study not just the star itself, but also the environment it existed in, providing a fuller picture of its life and death. But stellar echoes don't just tell us about individual stars, they also help us understand the broader processes that shape galaxies. By studying multiple echoes from different stars, scientists can track how elements are distributed across space and how they contribute to the formation of new stars and planets. It's a way of connecting the dots between the past and the present, showing how the universe recycles its materials over billions of years. As we explore these cosmic echoes, we're reminded that the universe is full of stories waiting to be uncovered. Each echo is a snapshot of a moment in time, a fleeting glimpse into the life of a star that once burned brightly. And as we piece together these echoes, we gain a deeper understanding of the forces that shape the cosmos. Next, we'll dive into the dynamic world of supermassive star clusters, where multiple massive stars are born together, creating some of the most energetic and fascinating regions in the universe. Stay tuned as we uncover how these clusters influence the evolution of galaxies. Now, let's turn our attention to one of the most awe-inspiring sights in the cosmos: supermassive star clusters. Picture this, a dense, swirling cloud of gas and dust where gravity pulls together massive amounts of material, igniting the birth of not just one, but dozens or even hundreds of supermassive stars all at once. These clusters are like cosmic nurseries on steroids, where the most massive stars in the universe come to life in a dazzling display of energy and light. Supermassive star clusters form in some of the most extreme environments in space, often within the hearts of massive molecular clouds. These clouds are so dense and packed with material that they create the perfect conditions for star formation on a grand scale. As gravity works its magic, pulling gas and dust together, pockets of material collapse under their own weight, heating up until nuclear fusion ignites and new stars are born. But unlike smaller star clusters where only a few massive stars might form, supermassive star clusters are dominated by these giants, creating a hotbed of stellar activity. The dynamics within these clusters are nothing short of chaotic. With so many massive stars packed into a relatively small space, their intense radiation and powerful stellar winds collide, creating a turbulent environment. These interactions can trigger even more star formation as shockwaves compress nearby gas clouds, setting off a chain reaction of stellar births. At the same time, the sheer gravitational pull of so many massive stars can warp the fabric of space around them, influencing the orbits of nearby stars and even entire star systems. But the impact of supermassive star clusters extends far beyond their immediate surroundings. These clusters play a crucial role in shaping the evolution of galaxies. The massive stars within them burn brightly but briefly, ending their lives in spectacular supernovae that scatter heavy elements like iron, gold, and uranium across the cosmos. These elements become the building blocks for new stars, planets, and even life itself. In this way, supermassive star clusters are like cosmic forges, recycling material and enriching the galaxy with the ingredients needed for future generations of stars and planets. What's more, the energy released by these clusters can drive galactic winds, powerful outflows of gas that can sweep across entire galaxies. These winds can regulate star formation by clearing out gas and dust, preventing new stars from forming too quickly. In some cases, they can even strip galaxies of their material, leaving behind a trail of cosmic debris. This delicate balance between creation and destruction is one of the key ways supermassive star clusters influence the life cycle of galaxies. As we explore these incredible clusters, we're reminded of the interconnectedness of the universe. From the birth of stars to the evolution of galaxies, supermassive star clusters are a testament to the dynamic and ever-changing nature of the cosmos. They show us how the smallest processes, like the collapse of a gas cloud, can have far-reaching consequences, shaping the universe on the grandest scales. Next, we'll delve into the intriguing phenomenon of stellar vampirism, where some supermassive stars siphon material from their companions, altering their life cycles in dramatic ways. Stay tuned as we uncover the secrets of these cosmic thieves. Now, let's shift our gaze to a phenomenon that sounds like it's straight out of a cosmic thriller: stellar vampirism. Imagine a supermassive star locked in a gravitational dance with a smaller companion star. Over time, the more massive star begins to siphon material from its partner, growing larger and more powerful while its companion slowly withers away. This isn't just a dramatic cosmic event. It's a real process that can dramatically alter the life cycles of both stars involved. In binary star systems, where two stars orbit each other, stellar vampirism occurs when one star's gravity becomes strong enough to pull material from the other. This often happens when the more massive star evolves faster, expanding into a giant or supergiant phase. As it grows, its outer layers become less tightly bound, making it easier for its companion to steal material. In some cases, the smaller star might even spiral closer, intensifying the transfer of material. The consequences of this behavior are profound. For the star doing the siphoning, the influx of fresh material can reignite nuclear fusion, extending its lifespan and potentially transforming it into an even more massive star. This can lead to spectacular outcomes, such as the star becoming a luminous blue variable or even a candidate for a future hypernova. On the flip side, the star losing material can be stripped down to its core, drastically shortening its life and altering its eventual fate. But the effects of stellar vampirism don't stop there. The stolen material often forms an accretion disk around the more massive star, a swirling ring of gas and dust that can emit intense radiation. This disk can also give rise to powerful jets of particles, which can influence the surrounding space and even trigger new star formation in nearby gas clouds. What's truly fascinating is how this process can create some of the most extreme objects in the universe. For example, if the siphoning star is already a supermassive star, the added material can push it toward a catastrophic collapse, potentially forming a black hole. Meanwhile, the stripped-down companion might end its life as a white dwarf or neutron star, depending on its initial mass. Stellar vampirism also has broader implications for the evolution of star systems and galaxies. By redistributing material and energy, these interactions can influence the chemical makeup of the surrounding space, seeding it with heavy elements that will eventually form new stars and planets. In this way, stellar vampirism is not just a destructive process, it's also a creative one, shaping the cosmic landscape in ways we're only beginning to understand. As we peel back the layers of this phenomenon, we're reminded of the delicate balance that governs the lives of stars. From the smallest interactions to the grandest transformations, the universe is a place of constant change, where even the most seemingly destructive processes can lead to new beginnings. Next, we'll explore the mysterious shadows cast by supermassive stars, revealing how these cosmic giants can influence their surroundings in unexpected ways. Stay with us as we uncover the secrets of these stellar silhouettes. Now, let's turn our attention to a phenomenon that feels almost like a cosmic art project: supermassive star shadows. Picture this: a colossal star blazing with unimaginable energy, casting its light across vast clouds of dust and gas. But instead of simply illuminating these clouds, the star's light creates intricate shadows, painting the cosmos with breathtaking patterns. These shadows aren't just beautiful, they're also a window into the nature of the stars themselves. When a supermassive star shines, its light doesn't travel unobstructed. Instead, it encounters dense regions of dust and gas, which block some of the light and create shadows on the material behind them. These shadows can stretch for light years, forming shapes that resemble towering pillars, swirling spirals, or even delicate filaments. The result is a stunning interplay of light and darkness, a celestial dance that reveals the structure of the surrounding interstellar medium. But how do astronomers observe these shadows? It's all about the contrast. The bright light from the supermassive star illuminates the dust clouds, while the shadows stand out as darker regions against this glowing backdrop. By studying these shadows, scientists can map the distribution of dust and gas in the area, gaining insights into the density, temperature, and composition of these cosmic clouds. This information is crucial for understanding how stars and planets form, as these clouds are often the birthplaces of new stellar systems. What's even more fascinating is what these shadows can tell us about the supermassive stars themselves. The size, shape, and intensity of the shadows depend on the star's luminosity, distance, and the properties of the surrounding dust. By analyzing these factors, astronomers can estimate the star's energy output and even infer details about its life cycle. For example, a star casting long, sharp shadows might be in a stable phase, while one with more diffuse shadows could be undergoing dramatic changes, such as shedding its outer layers or nearing the end of its life. These shadows also play a role in the larger cosmic ecosystem. As the light from the supermassive star interacts with the dust clouds, it can heat the material, triggering chemical reactions that lead to the formation of complex molecules. Over time, this process can influence the evolution of the surrounding region, potentially setting the stage for new star formation. In this way, the shadows cast by supermassive stars aren't just passive features, they're active participants in the ongoing story of the universe. As we marvel at these cosmic silhouettes, we're reminded of the intricate connections that bind the universe together. From the smallest grains of dust to the most massive stars, every element plays a part in shaping the cosmos. And by studying these shadows, we gain a deeper appreciation for the beauty and complexity of the stellar giants that light up the night sky. Next, we'll dive into the rhythmic oscillations of supermassive stars, uncovering how these pulsations reveal the secrets hidden within their cores. Stay tuned as we explore the heartbeat of these cosmic giants. Now, let's shift our focus to a phenomenon that gives supermassive stars a kind of cosmic heartbeat: stellar oscillations. Imagine a star not as a static, unchanging object, but as a dynamic, pulsating entity, expanding and contracting in rhythmic cycles. These oscillations, much like the vibrations of a musical instrument, carry valuable information about what's happening deep within the star's core. Supermassive stars are not just massive in size, they're also incredibly complex. Their interiors are a swirling mix of intense heat, pressure, and nuclear reactions, all working together to keep the star shining. But these internal processes don't stay hidden. Instead, they manifest as oscillations on the star's surface, causing it to vibrate in predictable patterns. These vibrations can range from subtle ripples to dramatic pulsations, depending on the star's size, age, and internal structure. So, how do astronomers detect these oscillations? It's all about precision. Using advanced instruments like space-based telescopes, scientists measure tiny changes in a star's brightness or surface temperature. These changes correspond to the star's oscillations, revealing a kind of stellar fingerprint. By analyzing these patterns, astronomers can peer into the star's interior, much like how geologists use seismic waves to study Earth's inner layers. What makes these oscillations so valuable is the wealth of information they provide. For instance, the frequency and amplitude of the vibrations can tell us about the star's density, temperature, and even its chemical composition. A star with rapid, high-frequency oscillations might have a dense core, while one with slower, more irregular pulsations could be undergoing significant changes, such as burning through its fuel reserves or preparing for a dramatic transformation. But the insights don't stop there. Stellar oscillations also help astronomers understand the life cycles of supermassive stars. By tracking how these vibrations change over time, scientists can predict how a star will evolve, whether it will end its life in a spectacular supernova or collapse into a black hole. This information is crucial for building accurate models of stellar evolution and understanding the broader processes that shape galaxies. Interestingly, these oscillations aren't just a one-way street. The vibrations can also influence the star's surroundings, creating ripples in the surrounding gas and dust. In some cases, these ripples can trigger the formation of new stars or even planets, adding another layer of complexity to the star's role in the cosmic ecosystem. As we explore the rhythmic pulsations of supermassive stars, we're reminded of the delicate balance that governs the universe. From the smallest vibrations to the most massive explosions, every movement tells a story. And by listening to the oscillations of these stellar giants, we gain a deeper understanding of the forces that shape the cosmos. Next, we'll venture into the glowing nebulae created by supermassive stars, uncovering how these cosmic clouds become the birthplaces of new stars and planets. Stay tuned as we explore the stellar nurseries that light up the universe. Now, let's turn our attention to one of the most visually stunning phenomena in the cosmos: supermassive star nebulae. These glowing clouds of gas and dust are more than just beautiful cosmic decorations. They're the result of the immense power and influence of supermassive stars. When a supermassive star shines, it doesn't just emit light, it releases an incredible amount of radiation and powerful stellar winds. These winds, made up of charged particles, blast outward at tremendous speeds, pushing against the surrounding gas and dust. Over time, this interaction creates vast, glowing structures known as nebulae. These nebulae can stretch for light years, forming intricate shapes and patterns that light up the darkness of space. But these nebulae aren't just passive byproducts of a star's energy. They play a crucial role in the life cycle of stars. The intense radiation from the supermassive star heats up the surrounding gas, causing it to glow and ionize. This process can trigger the collapse of nearby gas clouds, compressing them until they reach the density needed to form new stars. In this way, supermassive stars act as cosmic architects, shaping the birthplaces of future stellar generations. The stellar winds from these massive stars also carve out cavities within the nebulae, creating regions of lower density. These cavities can become the sites of intense star formation, as the pressure from the winds compresses the surrounding material, encouraging it to clump together and ignite into new stars. It's a cosmic domino effect where the actions of one star set off a chain reaction that leads to the creation of many more. Interestingly, the composition of these nebulae can also tell us a lot about the supermassive stars that created them. As the star burns through its fuel, it fuses heavier elements in its core. When these elements are expelled into space through stellar winds or supernova explosions, they become part of the nebula's makeup. This means that the gas and dust in these nebulae are often rich in elements like carbon, oxygen, and nitrogen, ingredients essential for the formation of planets and potentially life. The role of supermassive star nebulae extends beyond star formation. They also serve as cosmic recycling centers, redistributing material throughout the galaxy. When a supermassive star eventually dies in a spectacular explosion, the nebula it leaves behind becomes a reservoir of raw materials, ready to be incorporated into new stars, planets, and even living organisms. As we marvel at the beauty of these glowing clouds, we're reminded of the interconnectedness of the universe. From the birth of a single supermassive star to the creation of countless new worlds, every element plays a part in the grand cosmic dance. Next, we'll explore how some supermassive stars act as cosmic timekeepers, their regular pulsations helping astronomers measure the vast scales of time and distance in the universe. Stay tuned as we uncover the rhythmic secrets of these stellar giants. Now, let's shift our gaze to a fascinating role that some supermassive stars play in the cosmos' stellar timekeepers. These massive stars, with their rhythmic pulsations and rotations, serve as natural clocks, helping astronomers measure time and distance across the vast expanse of the universe. Imagine a star that beats like a heart, expanding and contracting in a steady, predictable rhythm. These pulsating supermassive stars, known as Cepheids variables, are incredibly valuable to scientists. Their brightness changes in a regular cycle, and by studying these cycles, astronomers can determine the star's intrinsic brightness. Once they know how bright the star truly is, they can compare it to how bright it appears from Earth and calculate its distance. This method, called the standard candle technique, has been instrumental in mapping the universe and understanding its scale. But the usefulness of these stellar timekeepers doesn't stop there. Some supermassive stars rotate at incredibly consistent speeds, acting like cosmic lighthouses. As they spin, they emit beams of radiation that sweep across space, creating regular pulses of light or radio waves. These pulsars, as they're called, are so precise that their pulses can be used to measure time with incredible accuracy. In fact, some pulsars are so reliable that they rival atomic clocks here on Earth. These pulsating and rotating stars also provide insights into the structure of the universe. By observing how their light is affected by the gravitational pull of nearby objects, astronomers can detect the presence of planets, black holes, or even dark matter. This makes supermassive stars not just timekeepers, but also cosmic detectives, uncovering hidden secrets of the universe. What's truly remarkable is how these stars bridge the gap between the microscopic and the cosmic. Their regular rhythms allow us to measure distances spanning millions of light years, while their precise pulses help us understand the fabric of space-time itself. In a universe that often feels chaotic and unpredictable, these stellar timekeepers offer a sense of order and reliability. As we continue our journey through the strange behaviors of supermassive stars, we'll next explore the eerie remnants they leave behind, stellar ghosts that continue to influence the cosmos long after their fiery lives have ended. Stay with us as we uncover the haunting legacy of these celestial giants. Now, let's step into the shadowy realm of stellar remnants, where the echoes of supermassive stars linger long after their fiery demise. These cosmic ghosts, the remnants of once mighty stars, continue to shape the universe in profound and often eerie ways. When a supermassive star exhausts its fuel and collapses, it doesn't simply vanish. Instead, it leaves behind a dense, enigmatic remnant that can take one of two forms: a neutron star or a black hole. Neutron stars are the incredibly dense cores left behind after a supernova explosion. Imagine squeezing the mass of our Sun into a sphere no larger than a city. These objects are so dense that a single teaspoon of neutron star material would weigh billions of tons. But their influence doesn't stop at their staggering density. Neutron stars often spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses, creating the pulsars we discussed earlier. Black holes, on the other hand, are even more mysterious. When a supermassive star collapses under its own gravity, it can form a black hole, a region of space where gravity is so intense that not even light can escape. These cosmic voids are invisible, but their presence is felt through their gravitational pull. Black holes can warp space-time, bend light, and even pull in nearby stars and gas, creating swirling disks of superheated material that glow brightly before disappearing into the abyss. What's truly fascinating is how these stellar ghosts continue to influence their surroundings. Neutron stars, for example, can power some of the most energetic phenomena in the universe, such as gamma-ray bursts. These bursts are so intense that they can outshine entire galaxies for a brief moment, releasing more energy in seconds than our Sun will emit in its entire lifetime. Black holes, meanwhile, can shape entire galaxies. The supermassive black holes at the centers of galaxies act as gravitational anchors, influencing the orbits of stars and gas clouds and even regulating star formation. Even in death, these remnants of supermassive stars play a vital role in the cosmic ecosystem. They are the ultimate recyclers, transforming the material of dead stars into the building blocks for new ones. The heavy elements forged in the hearts of supermassive stars and scattered by their explosive deaths are eventually incorporated into new stars, planets, and even life itself. As we move forward, we'll explore another intriguing phenomenon, stellar echo chambers, where the light and energy of supermassive stars bounce off surrounding structures, creating a cosmic symphony of echoes. Stay with us as we uncover how these echoes reveal the secrets of the universe. Now, let's turn our attention to a phenomenon that feels almost poetic in its cosmic beauty: stellar echo chambers. Imagine a supermassive star unleashing a burst of light or radiation into the void. Instead of fading into obscurity, this energy bounces off nearby clouds of dust and gas, creating ripples of light that travel through space like echoes in a vast interstellar canyon. These echoes aren't just stunning to observe, they're also invaluable tools for astronomers. When a supermassive star explodes or emits a powerful flare, the light from that event doesn't just travel in a straight line. It interacts with the surrounding interstellar medium, reflecting off dust clouds and other structures. These reflections, or echoes, can be detected by telescopes long after the original event has faded. By studying these echoes, scientists can piece together the history of the star's explosive behavior, even if the star itself is no longer visible. One of the most remarkable aspects of stellar echo chambers is how they allow us to study events that happened in the distant past. For example, if a supermassive star exploded hundreds or even thousands of years ago, the light from that explosion might have already passed Earth. But the echoes of that light, bouncing off distant dust clouds, can still reach us today. It's like having a cosmic time machine, giving us a glimpse into the universe's history. These echoes also provide clues about the environment surrounding the star. The way light reflects off dust clouds can reveal the composition, density, and even the motion of these clouds. This information helps astronomers understand the conditions in which stars form and evolve, shedding light on the life cycles of supermassive stars and their impact on the galaxy. But perhaps the most fascinating aspect of stellar echo chambers is their role in uncovering the secrets of the universe's most extreme events. For instance, echoes from gamma-ray bursts, some of the most energetic explosions in the cosmos, can help scientists measure the distances to faraway galaxies and study the properties of the early universe. These echoes act as cosmic messengers, carrying information across vast stretches of space and time. As we continue our journey through the strange behaviors of supermassive stars, we'll next explore the regions where these colossal stars are born, the supermassive star nurseries. These dense, chaotic environments are the cradles of cosmic giants, and they hold the key to understanding how the universe's most massive stars come to life. Stay with us as we venture into these stellar birthplaces. Now, let's step into the cosmic cradles where the universe's most massive stars are born, the supermassive star nurseries. These regions are unlike anything else in space, dense, turbulent, and brimming with raw materials that fuel the birth of stellar giants. Picture vast molecular clouds, colossal structures of gas and dust stretching across light years. Within these clouds, gravity begins its delicate dance, pulling together immense amounts of material until the pressure and temperature reach a tipping point. And just like that, a supermassive star ignites, lighting up the darkness with its brilliance. The conditions required for the formation of supermassive stars are extreme. These stars don't form in isolation. They emerge in the heart of the densest molecular clouds, where the sheer amount of gas and dust creates the perfect environment for their birth. Temperatures in these regions can plummet to just a few degrees above absolute zero, allowing gravity to take hold and compress the material into a growing stellar core. But it's not just about density. These nurseries are also chaotic, with turbulent flows of gas and magnetic fields shaping the process. What makes these nurseries truly fascinating is their role in galactic evolution. Supermassive stars are rare, but their impact is profound. As they form, they begin to influence their surroundings almost immediately. Their intense radiation and powerful stellar winds carve out cavities in the molecular clouds, triggering the formation of new stars nearby. In a way, these stars act as cosmic sculptors, shaping the very fabric of their galactic neighborhoods. But the story doesn't end there. Supermassive stars are also key players in the chemical evolution of galaxies. Through their life cycles, they forge heavy elements in their cores, which are later scattered into space through stellar winds or explosive deaths. These elements become the building blocks for new stars, planets, and even life itself. Without supermassive stars, the universe as we know it would look very different. As we peer into these stellar nurseries, we're not just witnessing the birth of stars, we're uncovering the origins of the cosmos itself. These regions hold the secrets to how galaxies grow, evolve, and transform over billions of years. And as we continue our exploration, we'll next turn our attention to another remarkable aspect of supermassive stars: their role as cosmic time capsules, preserving clues about the early universe. Stay with us as we unravel more mysteries of these celestial giants. Now, let's shift our gaze to a truly remarkable aspect of supermassive stars: their ability to act as cosmic time capsules. These stellar giants hold within them secrets of the early universe, preserving clues about the conditions and elements that existed billions of years ago. Imagine a star as a living archive, its composition a snapshot of the cosmos at the time of its birth. Supermassive stars are like celestial historians. Their cores are forged from the primordial gas and dust that filled the universe shortly after the Big Bang. As these stars form, they lock in the chemical fingerprints of their surroundings, capturing the elemental makeup of the cosmos in its infancy. This makes them invaluable to astronomers who study their light to decode the history of the universe. One of the most fascinating ways scientists study these stars is through spectroscopy. By analyzing the light emitted by supermassive stars, astronomers can identify the elements present in their atmospheres. Elements like hydrogen, helium, and traces of heavier metals such as iron and carbon reveal not only the star's composition but also the conditions of the early universe. For example, the presence of certain elements can tell us about the processes that occurred in the first generations of stars, long before our own sun was born. But the story doesn't stop there. Supermassive stars also play a crucial role in the cosmic cycle of matter. As they live and die, they scatter these elements back into space through stellar winds or explosive supernova. This enriched material becomes the building blocks for new stars, planets, and even life. In a way, these stars are not just time capsules, they are also the architects of the universe's future. What makes this even more extraordinary is that some of the oldest supermassive stars we observe today are relics from a time when the universe was vastly different. Their light has traveled billions of years to reach us, offering a glimpse into a younger, more chaotic cosmos. By studying these ancient stars, astronomers can piece together the timeline of cosmic evolution, from the first moments after the Big Bang to the complex galaxies we see today. As we continue to explore the mysteries of supermassive stars, we'll next turn our attention to another intriguing phenomenon: the halos of gas and dust that surround these celestial giants. Stay with us as we uncover how these halos shape the life cycles of stars and influence the cosmos around them. Now, let's turn our attention to the mesmerizing halos that envelop some supermassive stars. These halos, made up of gas and dust, are not just beautiful to observe, they play a critical role in the life and evolution of these cosmic giants. Picture a supermassive star as a glowing beacon, surrounded by a shimmering veil of material that stretches far into space. This halo isn't just a passive decoration, it's an active participant in the star's story. These halos form as supermassive stars release vast amounts of material into their surroundings. Through powerful stellar winds or explosive events, the star ejects gas and dust, creating a swirling cloud that encircles it. Over time, this material accumulates, forming a halo that can extend for light years. The composition of these halos is a mix of elements forged in the star's core, including heavier metals like iron and carbon, as well as lighter elements like hydrogen and helium. This mix provides a snapshot of the star's internal processes and the conditions in its immediate environment. But what makes these halos truly fascinating is their role in the star's life cycle. As the halo grows, it can influence the star's evolution in several ways. For one, it acts as a reservoir of material that can fall back onto the star, fueling further growth or triggering new phases of activity. In some cases, the halo can also shield the star from external forces, such as radiation or gravitational interactions with nearby objects. This protective barrier can extend the star's lifespan, allowing it to burn brighter and longer than it might otherwise. Additionally, these halos play a key role in the broader cosmic ecosystem. The material within them doesn't just stay put, it can be pushed outward by the star's radiation or stellar winds, spreading into the surrounding space. This enriched material becomes the raw ingredients for new stars, planets, and even the building blocks of life. In this way, supermassive stars and their halos are not just isolated phenomena. They are integral to the ongoing cycle of creation and destruction in the universe. As we marvel at these halos, we're reminded of the interconnectedness of cosmic processes. Each halo tells a story of a star's past, present, and future, offering clues about its origins and its ultimate fate. Next, we'll dive into the spectacular fireworks created by supermassive stars, where their explosive energy lights up the cosmos in ways that defy imagination. Stay tuned as we explore these dazzling displays of stellar power. Now, let's shift our gaze to one of the most breathtaking displays in the cosmos: stellar fireworks. Imagine a supermassive star as a cosmic artist, painting the universe with bursts of light and energy so intense they rival the brilliance of entire galaxies. These fireworks aren't just beautiful, they're a testament to the raw power and drama of supermassive stars. When a supermassive star reaches the end of its life, it doesn't go quietly. Instead, it often ends in a spectacular explosion known as a hypernova, or, in some cases, a gamma-ray burst. These events release an unimaginable amount of energy, more than our sun will produce in its entire lifetime, in just a matter of seconds. The sheer scale of these explosions is staggering. For a brief moment, a single star can outshine its entire host galaxy, lighting up the cosmos with a flash so bright it can be seen across billions of light years. But the fireworks don't stop there. Collisions between supermassive stars can also create dazzling displays. When two of these giants collide, the resulting explosion is nothing short of cataclysmic. The energy released during such an event can trigger shock waves that ripple through space, compressing nearby gas and dust and sparking the birth of new stars. These collisions are rare, but when they happen, they leave behind a legacy of light and energy that can be observed for millennia. The visual impact of these stellar fireworks is nothing short of awe-inspiring. From Earth, we see them as bright flashes or glowing remnants that linger in the night sky. These remnants, often called supernova remnants or gamma-ray burst afterglows, can take on intricate shapes and colors, resembling cosmic fireworks frozen in time. They serve as a reminder of the star's final act, a fleeting yet unforgettable performance on the grand stage of the universe. Beyond their beauty, these events have profound implications for the cosmos. The energy and material released during these explosions enrich the surrounding space, seeding it with heavy elements like gold, platinum, and uranium. These elements, forged in the hearts of supermassive stars, become the building blocks for new stars, planets, and even life itself. In this way, the fireworks of supermassive stars are not just an end, they are also a beginning. As we marvel at these celestial displays, we're reminded of the dynamic and ever-changing nature of the universe. Each explosion, each collision, is a moment of transformation, a reminder that even the mightiest stars are part of a larger cosmic dance. Next, we'll explore how supermassive stars cast shadows on nearby planets, shaping their environments in ways that could influence the search for life beyond Earth. Stay with us as we uncover more wonders of these cosmic giants. Now, let's turn our attention to a phenomenon that might sound like something out of science fiction: supermassive star shadows on planets. Picture this: a supermassive star millions of times brighter than our Sun, casting a shadow so vast it envelops an entire planet. This isn't just a dramatic visual, it's a real cosmic event with profound implications for the planets caught in its path. When a supermassive star's light is blocked by a planet, it creates a shadow that can stretch across vast distances. This shadow isn't like the fleeting darkness we experience during a solar eclipse. Instead, it can last for years, decades, or even longer, depending on the star's size and the planet's orbit. For any planet within this shadow, the effects can be dramatic. The sudden drop in light and heat can drastically alter the planet's climate, potentially turning a once habitable world into a frozen wasteland. On the flip side, if the planet is too close to the star, the intense radiation outside the shadow zone could make life impossible, leaving only a narrow band of potential habitability. But the story doesn't end there. These shadows can also act as cosmic magnifying glasses. As the star's light bends around the planet, it can create a lensing effect, amplifying the light from distant objects behind it. This phenomenon gives astronomers a unique tool to study exoplanets and their atmospheres in greater detail. By analyzing the light that passes through these shadows, scientists can detect the presence of water, oxygen, and other key ingredients for life. The implications for exoplanet research are enormous. Supermassive star shadows provide a natural laboratory for studying how extreme conditions affect planetary environments. They help us understand the delicate balance required for a planet to support life and offer clues about where to look for habitable worlds beyond our solar system. These shadows also challenge our assumptions about habitability, reminding us that the universe is full of surprises. As we explore these cosmic shadows, we're reminded of the intricate interplay between stars and planets. Each shadow tells a story of light, darkness, and the delicate dance of celestial bodies. Next, we'll venture into the final resting places of supermassive stars, stellar graveyards where the remnants of these giants continue to shape the cosmos. Stay with us as we uncover the mysteries of these cosmic tombs. Now, let's journey to the final resting places of supermassive stars, stellar graveyards, where the remnants of these cosmic giants continue to shape the universe long after their fiery deaths. These graveyards are not quiet or still, they are dynamic, powerful, and full of surprises. When a supermassive star exhausts its fuel, it doesn't simply fade away. Instead, it leaves behind a legacy that can take the form of black holes, neutron stars, or even dense clusters of stellar remnants. Each of these remnants carries the imprint of the star's immense power and continues to influence the cosmos in profound ways. Black holes, for instance, are one of the most dramatic outcomes of a supermassive star's demise. When a star collapses under its own gravity, it can form a black hole, a region of space where gravity is so intense that not even light can escape. These cosmic behemoths are far from dormant. They actively pull in surrounding matter, creating swirling disks of gas and dust that heat up to incredible temperatures, emitting powerful radiation. Black holes can also distort space-time itself, bending light and creating gravitational waves that ripple across the universe. These waves, detected by observatories here on Earth, provide us with a new way to study the universe and understand the violent events that shape it. Neutron stars are another fascinating remnant of supermassive stars. These incredibly dense objects are born from the explosive deaths of stars that aren't quite massive enough to form black holes. A neutron star packs the mass of our Sun into a sphere only about 12 miles across. Imagine squeezing Mount Everest into a sugar cube. That's the kind of density we're talking about. Neutron stars spin rapidly, some completing hundreds of rotations every second, and emit beams of radiation that sweep across space like cosmic lighthouses. These pulsars, as they're called, are invaluable tools for astronomers, helping us measure distances in the universe and test the laws of physics under extreme conditions. In some cases, the remnants of supermassive stars gather together in dense clusters, creating stellar graveyards that are teeming with activity. These clusters can contain hundreds or even thousands of neutron stars and black holes, all orbiting each other in a complex gravitational dance. Over time, these objects can collide, producing bursts of energy that light up the cosmos and send ripples through space-time. Such collisions are thought to be the source of some of the most energetic events in the universe, including gamma-ray bursts and the creation of heavy elements like gold and platinum. The influence of these stellar graveyards extends far beyond their immediate surroundings. They act as cosmic laboratories, offering insights into the behavior of matter under extreme conditions and the processes that drive the evolution of galaxies. By studying these remnants, scientists can piece together the life cycles of stars, from their birth in dense molecular clouds to their explosive deaths and the legacy they leave behind. As we explore these stellar graveyards, we're reminded that even in death, supermassive stars continue to shape the universe. Their remnants are not just relics of the past, they are active participants in the ongoing story of the cosmos. And with that, we've reached the end of our journey through the strange and fascinating behaviors of supermassive stars. From runaway stars to stellar graveyards, these cosmic giants never cease to amaze us with their power, complexity, and beauty. Thanks for joining us on this exploration of the universe's most extraordinary stars. Don't forget to like, subscribe, and hit the notification bell to stay updated on our next cosmic adventure. Until then, keep looking up. The universe has so much more to reveal. And so, we've reached the end of our cosmic journey through the 30 strange and awe-inspiring behaviors of supermassive stars. From runaway stars racing across galaxies to the explosive deaths that leave behind black holes and neutron stars, these celestial giants have shown us just how dynamic and unpredictable the universe can be. Each behavior we've explored, whether it's stellar cannibalism, magnetic monsters, or the haunting echoes of stellar explosions, reveals a piece of the puzzle that helps us understand the life cycles of stars and the forces that shape our cosmos. Supermassive stars are more than just distant points of light in the night sky. They are cosmic laboratories, teaching us about the extremes of gravity, the birth of elements, and the evolution of galaxies. Their strange behaviors challenge our understanding of physics and inspire us to keep pushing the boundaries of what we know. By studying these stars, we're not just learning about them, we're learning about the very fabric of the universe itself. But the story doesn't end here. The universe is vast and there's still so much we don't know. What other secrets do supermassive stars hold? Could their remnants, like black holes and neutron stars, hold clues to the origins of the universe or even the nature of space-time itself? The more we explore, the more questions we uncover, and that's what makes astronomy so thrilling. So, as we wrap up this journey, I want to leave you with this thought. The next time you look up at the night sky, remember that every star you see has a story to tell. Some of them are supermassive stars living out their lives in ways that defy imagination. What do you think we'll discover next about these cosmic giants? Let me know your thoughts in the comments below. I'd love to hear your ideas and questions. If you enjoyed this exploration of supermassive stars, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss out on our next cosmic adventure. Until then, keep your eyes on the stars and your curiosity alive. The universe is waiting to reveal its next great mystery. Thanks for watching, and I'll see you in the next video.